Yes, welcome, Professor Dukkipati.
Okay, everybody can hear me, or he's asking you need a more volume? Fine? Fine. It's fine, yeah. Okay. So, uh, this talk is about, I'll try to first explain some of the things. So, everybody knows the networks, right? There is a huge amount of relational data that is generated every time. Like, you share emails and Facebook and, telephone calls, and there's a huge networks are, being generated, right? So, we are talking about the community detection in networks. So community means that tightly interacting nodes in the network. Okay. This can be, if you know graph theory, you can treat it as a graph partitioning problem, right? That means that you want to find subgraphs, okay, such a way that uh, in that subgraph you have there are more connections and there is very less connection that is going out of that partition. Okay, and what is spectral graph algorithm? Why do we need a spectral theory? See, this graph partitioning problem is NP hard and it's very difficult to solve, right? So the spectral algorithms basically they'll provide you an approximate solution to this problem. Okay, so polynomial time algorithm, right? Spectrum means that you know that you calculate eigenvalues and eigenvectors, which can be done in polynomial time. Okay, then what is the statistical analysis? So you have approximate algorithm, right? And you want to know like how well it is doing, right? So there is one very beautiful result in spectral graph theory that is called the Cheetahs Inequality, and that gives you some kind of uh, guarantee on like how bad you are going to do. You are not going to do too bad if you apply a spectral clustering algorithm, right? But the kind of the approximation we are going to perform here is very crude approximation, in spite of fact that this inequality that will tell you that you are not doing too bad. Okay, but it will tell you that you are not doing too bad in terms of your optimization, but it will not tell you, it will not give you bound on what are the misclustered nodes, right? So you want to bound your error, right? So how do you bound your? So there is a result in machine learning that says that uh, under some constraints, uh, some constraint your error is constant, right? So, but these constraints are too hard, like it's not very unrealistic, right? So then people are okay with order n error, right? That means that your error is going in terms of order n. That means that n is the number of nodes. That is okay. So if your error is constant, that is called consistent, and if your error is going in terms of small o n, that is called weak consistent, right? So how do we establish these weak consistency of spectral algorithms for community detection? These results came reasonably recently that you can show that these algorithms are, these approaches are weak consistent. The problem is that there are some factors, right? Like some factor is that the factor you have to look for is that if your network is really dense, right? For this, most of this algorithm, it is easy to determine the community. But if the network becomes sparser and sparser, right? So it will become very hard for algorithms to find the community. So the factor is that how much you can weaken this factor, like how much sparse your network can be, still you can achieve a weak consistency. This is what we are going to see. Right? So this is a graph, and you have this. The aim is to partition a graph into k clusters, and throughout the talk, like for particularly these algorithms, you had to know k in advance, right? So the cluster properties are many edges within the clusters and very few edges between the clusters. So this is what we want to do. But you want to pose one more condition, that your cluster should be reasonably sized. You don't want like very few points to be there or something like that, right? So the partitioning objective is that cut across fewest edges possible, and also these clusters has to be reasonably sized. Okay. So why this is an interesting problem? Because the graph partitioning is NP hard, and if you want to do it as a brute force with small graph with 100 nodes, and this is what you get into. So then you get into heuristics, optimality, consistency, and efficiency. So we are going to concentrate on the consistency part here in this talk. Okay, why spectral methods? Because they give a nice approximation, nice in the sense that it leads to a polynomial time algorithms, and with some theoretical guarantees provided by the statistical analysis. So when I say statistical, you might think that where is the probability coming into picture? These are all deterministic algorithms. This is not a probabilistic algorithm. The probability is coming into picture because to bound the expected error. So we are not going to bound the error, but we are going to bound the expected error. So what we do is we'll create some kind of a random graph model. We'll sample graphs from this model and feed into your algorithm and calculate the error, right? So from the machine learning perspective, this is unsupervised learning algorithm, right? So for supervised learning algorithms, you know how to evaluate accuracy of your method, but unsupervised learning algorithms, you need different techniques, right? So what is this? That means that underlying object in the problem can be represented as matrices, and we know that graphs can be represented as the adjacency matrix, right, or incidence matrix. So eigenvalues and the eigenvectors of these matrices become a clue to this solution, right? This gives you a solution. So just by calculating some few eigenvectors, you can get the partitioning of a graph. Okay, so whatever we want to do, we want to get some money out of it, right? Like send. So can these make you rich? Can anybody tell me? Not Pata. Can anybody from the students? Have you heard of any stories? Huh? Huh? Page rank algorithms. Very good. So yes, it has made somebody very rich. And if you want to know the number, like really long time back, that is that number. That is 2006. The paper was written. This is a very beautiful paper. I want you to read. Okay, and also. Which I'm not going to mention, that the page rank and the spectral algorithms has very tightly related. Okay, so the kind of objectives we are going to define, right, has some relation to this page rank. Okay. Okay, so this is what I'm going to do. Quickly, I'm going to give some basic spectral graph theory because we have wide, really people from different domains, and I'll present the spectral algorithm, and then I'll just tell you that how, what is the kind of statistical analysis you need to establish these guarantees, and then I'll just mention about more complex graphs called hypergraphs. What you can do with this. Okay, spectral taxonomy is very well studied in machine learning, statistics, and theoretical computer science, and it has a very strong theoretical grounding. So basically, if you look at that graph, so if you have that kind of data and your k-means cannot find a good partitioning, but spectral clustering will be able to find these clusters, right? This kind of nonlinear clusters. Okay, but just now till now I was talking about network. I suddenly moved to data. So what is that? So every data can be looked at it as a network by calculating some kind of a distance between points, right? So that will become some kind of a weighted graph, right? So one of the very complicated network is the human brain, and and this is what we have. And what are the problems that are interest to neuroscientists? It looks like our brain is like there are some particular activities, right, or done by some particular neurons or particular regions, right? So neuroscientists, like by conducting some experiment, they extract they produce a lot of amount of data, right? So then they want to run some kind of clustering algorithm. They want to find the clusters. What are these sections of the brain doing some particular task, right? So, these community detection also has applications in these understanding the brain. Okay, so that means that model the structure and functional connectivity of brain regions as a brain network. So actually, if you read this 2013 paper, like people are observing this kind by performing this kind of by applying this kind of algorithm, and they are able to see the community structure in the brain networks. So we'll just move on with this. So what are the other applications? So it's very well known that the spectral clustering can be applied to image segmentation, like this is the Jitendra Malik's paper, and also social networks, and also the important thing is the detection of terrorist groups in the online and social networks. Apparently, this really happens now, right? Some intelligent agencies, they look at the social network, they'll try to analyze these things to find out, like, who are all linked to these things. So also epidemic spreading on the networks, that how the disease spread on the networks. So quickly, let's do some basic spectral graph theory to get into the problem, right? So here chi of g is chromatic number, like we are talking about a graph coloring problem. I just want to tell you that, like, how some of the properties of graphs can be linked to the eigenvalues of a graph adjacency matrix, right? So this is a result that says that only when G is complete and G has odd cycles, we have chromatic number is less than or equal to D max. Okay. Then I'll give you the result from numerical linear algebra that says that this is a Gershgorin theorem. This says that, so if you have a matrix, right, can you say that your eigenvalues are contained in particular region? Can you give a bounds? This is a very beautiful, very simple result, and actually easy to prove also. So saying that if you have a non-negative real matrix, all the eigenvalues are lie in a set. So here these are the entries. So basically you are looking at your AII, and you are looking at, you are summing up all the remaining entries in the matrix, and that's what this quantity is, right? So this is there. The reason why I'm mentioning is that one can show that your, so here is, so A is the adjacency matrix of graph. So suppose these are the eigenvalues of A, and then you have mu1 is less than or equal to D max. So since so why these eigenvalues are real? Because we have a symmetric matrix, right? Or adjacency matrix is a symmetric matrix, right? So we are dealing with a symmetric matrix, right? So one can prove this like using the Gershgorin theorem. And using these results, the previous result also can be proved using the Rayleigh principle, which we are going to use later. Okay, so one can establish that your this is the connection between your chromatic number and your first eigenvalue. Okay, I call it a first eigenvalue, mu1. So this is the connection between, so various properties of graphs can be linked to the eigenvalues of a graph. This is one example. Okay, let us look at quickly like what are the matrices that are related to graphs. So everybody, we all know that this is the adjacency matrix, and what else we have? We are going to see some more matrices. This is the degree matrix. So basically, degree matrix is that you just calculate the degree of each node and just put it in the diagonal, and elsewhere, everywhere else, you just have zeros. Okay. This is also we are going to use. And actually, in this talk, we are not going to deal with adjacency matrix. We are going to deal with some other matrix that is called, okay, incidence matrix. We all know is the Laplacian matrix. The Laplacian matrix is defined as L equal to D minus A. So this has some interesting properties. So why we don't deal with adjacency matrix is that Laplacian, when you use the Laplacian matrix, so it gives a nice connections to the objectives for the partitioning that we are going to pose, okay, which we are going to see. And we are also going to see normalized Laplacian. I'll tell you that how this comes, like this is I minus, this is the degree 1 by 2 and A this one. So usually I think in machine learning people, they usually use the normalized Laplacian. Right? So this is what graph Laplacian looks like. You have in the diagonal you have a degree, and if there is a connection between the two nodes, you have -1, otherwise this is 0. These are the properties. Now, say lambda 1, lambda 2, lambda n are eigenvalues of L. So the properties of this Laplacian is that L is symmetric, we all know. It's also positive semi-definite, right? And lambda 1 is always 0, and corresponding to the eigenvector is all ones. So basically the first so when I say first eigenvalue, that means that lambda 1, the smallest one, right? So usually the first eigenvector does not give you much information, has no information. Also you can, by calculating the second eigenvalue, if it is greater than 0, if and only if G is connected, right? And if your lambda k equal to 0 and till up to lambda 1, lambda 2, up to lambda k, you have 0 eigenvalues, then G has exactly k disjoint components, right? So these are like not very difficult to prove. So because we have this one, I'm defining my Laplacian as D minus A. So that's why you will get a minus. The reason is that actually in the statistical analysis, I have seen people working with the adjacency matrix, probably the pure graph theorists probably they use. I'll just, so this is the reason. I'll just go back. So if you calculate X transpose Lx, it gives you this value, right? This is, so that's why this is positive semi-definite. It's kind of gives you this quantity X transpose Lx gives you some kind of, what is the, some kind of conductance of a graph. Okay, I'll just quickly go back. Okay, so we have a graph partitioning problem. We want to create an objective. Say we want to get a partition. So let's look at the bipartitioning problem. You just want to create two parts of the graph, such a way that you have tightly connected components, and there are very few edges that are going across the these partitions, right? So let's try to create. So basically this delta V1 is a subset of V, delta V1 basically gives you the number of edges that are going out of this V1. The cut is nothing but the size of it, and the expansion cut, or it's a Chiggers cut, is defined as like cut divided by this. So basically these conditions you need to balance your partitions. You don't want too small partitions, right? And this is the ratio cut, and which is defined like this, right? So what we had to do, we had to find V1 such a way that, so if you look at the expansion cut, what we had to do, we had to find a V1 subgraph of V such a way that your cut has to be minimized, right? So our problem is going to be this. So you just have to find V1 such a way that you want to minimize this quantity. So ratio cut, there is a very close connection between these things, and we are also going to look at something called normalized cut. So this is called edge expansion, and also this is also called the Chiggers constant, right? This quantity, and this is if you optimize the ratio cut, this is the optimization problem you want, right? So everybody understood what we are trying to solve. We are trying to look at bipartitioning. Let's not worry about K. Just you want to find a subgraph of V1 such a way that this is maximal. Next, we'll try to pose this as a linear algebra problem. Okay. So, if you calculate x transpose x, x is any n-dimensional vector, this is what you get, right? So, x is an n-dimensional vector, and this is the quantity you get. Okay. Next, we are going to use some results. Don't worry about the top one, just look at this special case. Basically, what we have is that the second eigenvalue of a matrix or L, sorry, it's supposed to be L here, or any positive matrix, okay, positive symmetric matrix, is x transpose Lx divided by this. Like you are optimizing, you are finding minimum over the vectors that are orthogonal to 1 vector. Okay, so just take this as a result, right? Now, what we try to do is that, so I have a lambda 2, I'll try to pose the previous optimization problem in terms of this problem. Okay, I'm going to pose this as a optimizing this quantity. Okay. So before we get into that, this is the Chiggers constant and this is the Chiggers inequality, which I dwell on after I present the spectral algorithm. Oh, this is a very beautiful result. And one of the reasons why this spectral graph theory and this network analysis is so beautiful is because there are the three areas that is coming to. You have this numerical linear algebra, and you have combinatorics, and you have some bit of probability, right? These all interact very well. So for example, if you look at this is a pure linear algebra proof, but here you require some lot of combinatoric arguments. I think some various proofs also involve some probabilistic arguments for that. So Chiggers inequality you can write this way also, and I'll get back to this. Okay, so let's try to quickly get into the spectral graph algorithm. So you take the ratio cut, and our optimization. So we have to find V1 such a way that your ratio cut is minimized, right? That is our optimization problem. So now what I'll do is I'll define this crazy vector, okay, like this, okay. So basically, it's an n-dimensional vector, and if what is this y giving? It kind of telling you whether each node is there in a particular part. You have only two partitions. You have V1 and you have V1 complement. That's all. You have only two columns. So if the ith node is there in V1, so you just place this here, and if your ith node is not there, you just put this. This is an n-dimensional vector which represents which partition a node belongs to, right? So later I'm going to replace my V1 with Y. I can replace my V1 with Y. It's this vectorial representation, right? So one can show that if you define your matrix like this Y transpose Ly is nothing but your ratio cut. Okay. Now, so what is the optimization problem? Now it is simple. So instead of ratio cut, I can optimize. I can find a Y. okay, which is of this form that minimize y transpose Ly. Suppose this script y star is subset of all the subset of Rn such that is of this form. Okay, so you are looking at some crazy subset of Rn, right? So you want to optimize this quantity over this subset. So this is what you have. Your optimization problem is find y belongs to y star such a way that you have this. And this is a very difficult optimization problem because you are trying to find a y in a very complicated subset of Rn. So I just want to make some relaxation, right? So one relaxation I can make is, okay, instead of, the script y star is subset of Rn, okay? So instead of optimizing over that, I'm just going to optimize over whole Rn. What will happen? You get a trivial solution because your 1 transpose L1 is 0, right? So this is not a good relaxation. So I can get some good relaxation by observing that this y transpose 1, like y is defined as like previous slide, is equal to 0. That means that y is, so any vector that is defined like this is orthogonal to 1. Okay. So, sorry. Okay. So now instead of optimizing like this, I'm going to pose my optimization as this. Okay. So this is still a relaxation, but this is what I'm going to get. So what is the solution of that? From the Rayleigh principle, the solution is nothing but lambda 2, right? Solution in the sense that the minimum is lambda 2 and your solution is nothing but second eigenvector. So your y, the second eigenvector is the one which minimizes this quantity. Okay. So you can do it with the k-way partitioning also. So here the ratio cut for ratio cut for k partitioning is defined like this. It's a simple extension. Now instead of there we represented our like partition using a n-dimensional vector. Here we are going to represent using n by k dimensional vector, right? So this matrix you define like this, and one can show that y transpose y equal to identity matrix, and ratio cut is nothing but a trace of y transpose L y. So this is exactly I'm doing the same way. So our optimization problem is y belongs to y double star. That means that all the matrices that has a particular form, right? See, what does this matrix look like? It's a n by n, it has n rows. Each row corresponds to one node, each node, right? So, so it has, if it belongs to, you have k columns, like if it belongs to a particular column, nth column, in there you are putting a 1 by that quantity, everywhere else you have zeros. So here, so this is called the spectral relaxation. The spectral relaxation that you have is nothing but this one. You, instead of optimizing over y double star, you are going to optimize over Rn, provided that you give that, right? So you can take a guess what is the solution for this. The optimal the y that optimizes this problem is nothing but first k eigenvectors. So previously we had the first two eigenvectors, but anyway the first eigenvector doesn't give any information, so you have one eigenvector. Okay, so this is nothing but a matrix of k leading orthonormal eigenvectors of L. Okay. Okay, at this point I just want you to give you intuitive feeling what we are trying to do. Okay, so if you look at, so we have data points, right, that are the nodes, right? we are representing a network using a adjacency matrix or Laplacian. What is that giving, right? So that is giving, if you look at each row of adjacency matrix or Laplacian, each row correspond to a node, okay, a vertex, right? So you can consider that as a feature of that node. What is that feature? So everybody knows feature learning, right? Nowadays, like features. You know, from machine learning perspective, you know what is a feature. So the feature of that vertex is nothing but that row gives you the how it is connected to various other vertices, right? Intuitively, that is the adjacency matrix, right? And here, what are we getting? We are trying to find a n by k matrix, right? So this n by k matrix basically gives you the it's compressing, like it is projecting onto a lower dimensional feature space. So there, what is your feature vector size? N. Now what is your feature vector size? K. K is usually much smaller than n, right? So this is what we are doing, right? So here there's not much difference between the ratio cut and normalized cut. In the normalized cut, instead of like size of VL, you just have volume of VL. Volume is nothing but you just consider, you sum up all the degrees of those nodes. Okay. So the same thing you can do, and again here normalized cut is nothing but a trace of this quantity, and you'll also get the objective like this, something like this. Okay, so now you know why normalized Laplacian is defined like this. Okay, this is nothing but I minus that quantity. Okay. So here you are doing the same thing. That is the exact optimization problem. This is the relaxation of the problem. This is called the spectral relaxation. No. So previously I defined my y as this, right? Here I use the y double star, right? So my y double star is nothing but all the matrices that has this form, right? So all the matrices that has this form, right? See, if I change my VL, right, the matrix will change, right? So there is a one-to-one correspondence. So you just have to understand, like, there is a one-to-one correspondence between Y and a partition. So this is just capturing, like, where your node is, right? So maybe if you look at this is just a vector, n-dimensional vector, right? So this vector tells you that, so this is a bipartitioning, right? If a node is there, so it has only two non-zero values, right? If node is there in, if node is there in this V1, you just put it as this quantity, otherwise zero, okay? So basically there is a one-to-one correspondence between this vector and the partition, bipartitioning, and there you have one-to-one correspondence between the matrices and the partition. Okay. Now, what is a spectral clustering algorithm? That means that you just calculate the graph Laplacian and then compute a k leading vectors, okay, k leading eigenvectors, and then normalize the rows of y, because normalizing eigenvectors doesn't, you don't lose anything. And then to retrieve the partitions, you run your k-means clustering, right? So what are you doing? Now we are running a k-means on the k-dimensional space. Like previously we had an n-dimensional space. So basically the spectral method is giving you asks you to run a k-means on a k-dimensional space. That basically reduces your thing. Okay. So for example, if you have a bipartitioning problem, basically you are looking at your 1v2, right? So this is what you have. If you are looking at a bipartitioning problem, you just calculate a this eigenvector V2, because V1 anyway doesn't give you any information. So you have some numbers here, you normalize it by setting some kind of a threshold, right? Some threshold like this. You say that the whatever, so all these nodes, all these nodes above belongs to V1 and all the nodes belong to the other partition. You understand? Okay. What is the interpretation of Chiggers inequality? So you have Chiggers inequality says this, and here previously I have stated for a ratio this Chiggers cut. Here I'm just stating it for the normalized cut. It says that lambda 2, okay, so is less than or equal to this quantity. The Hg is the Chiggers constant. Okay, and only thing I am doing is I am replacing, instead of size of a partition, I am just replacing with volume. Okay, is less than or equal to square root of 2 lambda 2. Okay, so the first part of Chiggers inequality is very easy. Okay, the second part, just take a look at it. I'm going to state the second part of the Chiggers inequality like this. This is very important, right? So what it says is that you are applying a spectral algorithm to find a partition. So basically what you're doing is you're calculating a V2 and setting a some threshold, right? You are ordering these things and you're setting a some threshold. Based on that, you are dividing it. Right? So suppose you do that, right? If you get a S star, okay, that H of the Chiggers cut is less than or equal to square root of 2 lambda 2. Okay. So this H of S star is less than Chiggers constant or more than Chiggers constant? So Chiggers constant you get it by solving a exact problem, right? So H of S star you get it using a approximate method. So by using these things you can show that H of S star is nothing but this value, and I'll tell you this gives you this, like H of S star square is less than or equal to Hg, right? So what is this telling you? That if you look at this, all these quantities are between 0 and 1, and let me see whether I have something. Say you have 0 and 1, right? And your H of, this is your exact optimization problem. If you had solved, you would have been here, right? So H of S star is your approximate solution, and it cannot be very far away from this, right? If it is far away from this, this is going to be greater than this, right? If it is near to this, it will be here. Understand? So, spectral. So what Chiggers inequality gives you is the spectral algorithm is suboptimal only by a square root factor. Okay, that's what this result tell you. Okay. This is a simple thing, like you don't have to think too much, right? So everybody understood this? These quantities are between 0 and 1. Okay. Say this is my optimal value, right? If my H of S star is very far away, when I square it, what will happen? It will be still here, which is wrong according to Chiggers inequality, right? It has to be very near H of G, so that when you square it, it will come here. So that gives you some kind of guarantee. Okay, I'll just ignore this. Okay. So what is the error? So that gives you some guarantee on the optimal value, right? But it does not give you guarantee on the number of nodes that are misclustered, right? What are the misclustered? If you had solved the original optimization problem, what would have been your solution, right? So basically, this is the true membership matrix, and you just calculate you just take a Frobenius norm of these two matrices. So I am also adding a permutation matrix, because it doesn't matter. So if I get a solution, and I can always relabel them, right? So it is always, I say, if I call a partition 1 and 2, if my result give you 2 and 1, that should be the same, right? So that's why I'm multiplying with some permutation method. So now the story is that how we bound this, right? One bound you can get by, this is what you can do. So my spectral clustering is a very approximate algorithm, but what is the ideal case for when do you cluster very easily? If you have exactly in a bipartitioning problem, if you have tightly connected components, right? If you have two components, right? So that means that your matrix is nothing but some kind of a okay, put it here. Say suppose your adjacency matrix is like this, right? So you have some blocks here, and this is a 0, right? So this is your ideal case, right? So it looks like in an ideal case, the spectral algorithm gives you exact solution, right? Though it is approximate. So what are the arguments we are going to use to bound this error? What we'll do is, you consider this is the ideal case. You consider what our real world adjacency matrix or Laplacian is getting is perturbation of that, right? So you're just modifying, you're adding some more matrix, right? So when you perturb your matrix, what will happen? Your eigenvalues are they continuous? Do they change continuously? If you have a matrix, you calculate eigenvalues. What happens if you change a little bit a matrix? So I'm adding some quantities to your entries. What will happen? Your eigenvectors are actually continuous. Like they don't change too much. They change like continuously. But eigenvectors are not. They change really drastically, right? So, so what we look at is, you just take a symmetric matrix. You have one more perturbation matrix, and basically this is your ideal matrix, and you are just perturbing using H, and this is your real world matrix, right? And Weyls theorem gives you that what would be your eigenvalues when bounds on eigenvalues when you perturb them, right? But so, by the way, I'm going to give you some tools of trade for all these things. Though there are some complicated things, I'm going to explain to you. Okay. This Davis-Kahan theorem basically gives you bounds on how much when you perturb your matrix, how much your eigenvectors change. Okay. In terms of, this is eigengap. Okay. And how your eigenvalues are spread, and this is nothing but your that H, that is your perturbation matrix. Okay, so using these bounds, right? Now you understand the story. So we are looking at our real world matrix as a perturbation of the ideal matrix, which my spectral clustering would have solved perfectly. But in my real world, I don't have the perfect matrix. I have perturbation of that. But how I can solve that, right? So by getting the bounds on eigenvectors, basically you can try to get a bounds on your error, right? So one can show that this result, this is proved in NG and Jordan. Unfortunately, I think in NIPS they were not putting the appendix. You can never find this proof anywhere. So I try to work it out, and this is the error you get. Okay, so basically one can show that this is just a constant, right? But here you're saying that your real world matrix is not too far away from your ideal matrix, right? So this is not really great. So what else can we do? So then we have stochastic block model. That means the stochastic block model is that you assume that you know the communities, okay, and then here you have a random model, right? Say in the two partition case, and here you have the so basically you create a graph with high probability. You generate edges in the partition, and across the partition with very low probability. right? So basically, when you sample a graph from this random graph, what you get is some kind of a graph that has some kind of block structure. You understand? Maybe I'll. This is latent space model is a special case of stochastic block model. I can leave it. Okay. So the stochastic block model is that. So B is the K by K matrix. B is the N by K matrix. No, K by K matrix. Okay. That gives you the probabilities for the intercluster probabilities, and so this is Z is the N by K matrix, right? So using this, what you get is a random matrix, okay, which has some kind of a block structure, okay. The population version means that it's a random model, and your random variable is nothing but a sample here, okay. So here we are going to work with the Laplacian. So I'm not giving a I minus, right? So instead of looking at the lowest eigenvectors, we are going to look at the highest eigenvectors. Okay. So I'm giving you some results from which we have used to prove some results. Okay. So I'll try to give some techniques here. Okay. Even if you catch hold of some words, that will be great. Okay. So can we achieve a consistency results if we let the number of clusters grow with the number of nodes? Okay. So here we are also saying that till 2011, like we are not changing the number of clusters, right? Your number of clusters are not growing, but your number of nodes are growing, and asymptotically you try to give the error. But this is the first paper that has given the weak consistency result, where that, see, if your network is growing, do you expect your clusters also to grow, number of clusters? No? Yes. If you look at the Facebook, right? So as more and more people come, they form their own clusters, right? So allowing this is reasonably difficult to establish. Once you allow this, is reasonably difficult to establish. Okay. Block model, and I have already explained this. This is just a random graph model where that within the partition you generate with high probability, and with across the partition you generate with the very low probability. Okay, the strategy is like this. So given as Z, just choose B and define your population version of your adjacency matrix, and sample W from this random matrix. Okay, and then so see, W is not random. It's just a sample of sample graph, right? You can feed it to your spectral algorithm and calculate get Z dash, right? So your Z dash is the result that is given by your spectral algorithm. Z is the result that is actual result. Okay, we are assuming that we know the partitions, and we'll compare with our answer, right? So you calculate the error, you keep doing that, and you get a expected error since this is a probability model. So how do you go about it? So suppose you have these both the population version, and so you have sequence of Laplacian, both the observed and the population versions of Laplacians, and under the stochastic block model, what is the difference between the eigenvectors of these two? Okay. So the goal is to prove the spectral clustering is weakly consistent, and for this is what we had to look at. We had to look at the sample observed and the population versions of Laplacians, and show that under this block model, the eigenvectors do not change much, or do they converge? So proof sketch is like this. You bound the eigenvalues of these ln and this one, that gives you by Weyls theorem. But eigenvectors is very difficult, and then so these are the steps, right? So you bound the eigenvectors, right? And then bound the k-means error. K-means also is not perfect. It will never give you the exact result, right? So this is the bird's eye view. So what we show is that you have two Laplacians. One is the random model and a sample, observed one, right? And under this block model, as n tending to infinity, you try to give a bound on the Frobenius norm of the difference. Okay, and then you can always use this is true, and then Wales inequality gives you your bound on eigen values, and then use the Davis-Kahan theorem to bound the eigenvectors. Okay. This one. This Frobenius norm is, 2 norm is always less than or equal to Frobenius. 2 norm of any matrix. No, here, this one. Because, yeah, the reason is that Wales inequality needs a 2 norm. So you are changing from Frobenius norm to 2 norm. Because Wales inequality gives you in respect to 2 norm. So that's the thing. Okay. And it looks like you can never establish that this can happen. Okay. If I have observed this, I would have stopped working on this problem, but these people had found a way around it. Okay, that is a very beautiful technique, which I'll tell you. It looks like you can never establish this. The counter example is this, right? Once you have, it's a simple Bernoulli example, and which I will not go into details, but one can show that with this simple example, this actually this limit actually diverges. Okay. So what do you do? So what did these people do is, instead of bounding that L minus the script L, they bound this one, right? Because of this result. This is a nice thing. For a real symmetric matrix, lambda square is the eigenvalue of M and M, if and only if, so lambda or minus lambda is eigenvalues of M. So you can always move from M to M square. That's what they do. And this actually makes the proof really crazy, but so this is what we are going to do. So in the beginning of the talk, I talked about the sparsity. Sparsity is very important. Like, if you assume that reasonable sparsity, it's very easy to establish. So the sparsity factor is this, okay, this tau n. What is tau n? So minimum number of expected degree divided by max possible degree. So we are going to use this kind of sparsity. So we are establishing weak consistency where this quantity is 1 by root log n. So this is the one which we are going to work at. This is a reasonably tight, reasonably sparse graph, right? So this is the result one can prove. See, because the single else did not work, one can show that it diverges, but one can show that this can be established. Okay, with this, that's sparsity constant. So some of the tools are use a Borel-Cantali. I'll just will not mention about this. You all learned Borel-Cantali, right? So this also I'll skip. I'll just put the last result. So see here you need a Davis-Kahan theorem for the squared L. So it looks like you can also have a Davis-Kahan for the squared L, and so basically what it says that, see, these are the eigenvectors, right? So this can be bounded by the difference between these two, right? So one can show that as n tending to infinity, the eigenvectors of squared L of a population matrix and the observed matrix Laplacian will converge to the difference will be 0. Okay. So these are the standard things people are going to use: Davis-Kahan and the Wales theorem. So Davis-Kahan works with the Frobenius norm, Wales theorem works with the 2 norm. Okay. and then blah blah blah, then you can establish the convergence of eigenvectors and eigenvalues, right? And probably if you want to go through this paper and want to work out the proof, like probably you had to spoil your weekend, right? So you just start on the Saturday morning, maybe so Sunday night, probably you will be able to figure out this proof. Okay, and then you establish bounds and k-means, and then you get the result. So what is the result? I'll just quickly mention. So this is the misclustered, right? So this is basically order ON. So what are we doing? So under this sparsity, where your expected degree divided by your max degree is greater than or equal to 1 by square root n, right? Square root of log n. Then under some eigen gap, you can establish a weak consistency of a spectral cluster. So this is the result. Okay, now so the work we have done is that, so there are the networks which can I take 5 more minutes? So you have graphs like this, and you also have, so usually the interactions are not always two-way, right? They can be multiple ways. So for example, if you look at the Twitter networks or something like that, they're actually not graphs. There are hypergraphs, right? So what is a hypergraph? Hypergraph is nothing but, instead of, here edges means that you have two vertices. In the uniform hypergraph, that means that your each edge size is 3, okay? And the general hypergraph, your edge size can be anything, okay? So these are the actual complex networks. These are the real world networks that usually we deal with. So, okay. So if you are given these 3 uniform and hypergraphs, 3 uniform hypergraphs and the general hypergraphs, how do you get a community detection, okay? And one simple thing is that it's a 3 uniform graph, and you represent using what? Can you represent using what? In the graph, you can represent using a matrix. The 3 uniform graph, 3 tensor, right? And if you have 4 uniform graph, you have a 4 tensor. But hypergraph, you cannot even represent using a matrix, right? Because you have a. So even in the case of uniform hypergraphs, you don't deal with. So one can show that you can calculate some kind of eigenvalues and vectors, and you can solve this problem of tensors. In the case of tensors, it looks like this is a you do not have a polynomial time algorithm for calculating eigenvalues and vectors of the tensors, right? So what you do is you bring down this problem to a graph case and try to solve it. So hypergraphs, and there are a lot of applications like subspace clustering, motion segmentation, and image segment. So these techniques, the spectral methods for these hypergraphs have been there for some time, but without knowing any theoretical guarantees, and this is what we have established. So there are some references. So these are the papers which have used like hypergraphs in computer vision, right? But without knowing the any guarantees. So what we do this? So if you have a hypergraph, what we do is we kind of translate into a we represent using some kind of weighted graph. So obviously you are going to lose some information, right, when you do this, right? And in graph theory, you know that uniform these hypergraphs, there are some edge, these vertex expansions and star expansions of hypergraphs. There are some other. So this is a one kind of expansion, right? I'm representing my hypergraph using an approximate hypergraph. Now you can say that you are cheating. Now you are just solving a graph problem, and you are saying that you are just established a bond. The key is that our algorithm is still a spectral algorithm on a graph. Okay, I understand. I am trying to solve, but my stochastic block model is on the hypergraph, right? So since it is a hypergraph, I cannot represent using a matrix or tensor. So how do you come up with a block model. This is what we have done. So the way you can do it is, if you have a general hypergraph, you can represent using collection of 2 uniform, 3 uniform, 4 uniform, like this, right? So you have a max edge size, then you generate these things and then club them. So, okay. So in this approach, our random model is a hypergraph, but our spectral algorithm is on this one. So this is the result we have established under reasonable sparse conditions, and the hypergraph, general hypergraph partitioning can be done in. So hypergraph partitioning is weak consistent. That means that your error does not go beyond this. Here you also come across n max. N max is the max edge size, right? This is the result that we have established, right? So the story is that these methods have been used by computer vision people for several times. This is the first time we could give some kind of guarantee that it's a weak consistent. Your approximate method is a weak consistent. Some recent work, we have also worked on the uniform hypergraph partitioning. So what happens is that your matrices are two hues, right? So there are really nice sampling methods in numerical linear algebra, which are very very much used in machine learning community. So if you have a huge matrix or a huge tensor, right? Don't work with the whole matrix. You just sample some columns or take a block of a matrix, right? In a clever way, such a way that you can get a reasonable result. These are called the Nystrom and column sampling kind of method. So we have also established this weak consistency results for using the sampling techniques, right? What happens with the sampling? With the sampling, you can calculate your spectral algorithm is much faster because you are using a smaller matrices and smaller thing. And this is, I don't know whether you heard of this compressive spectral clustering, like graph signal processing. This is some new area that evolved in signal processing, and one can show that using these methods, you can actually see your calculating eigenvectors is still a polynomial time, right? It's reasonably, if you have a really huge matrix, it's a lot of computational load. One can show that you can actually, this result appeared in one of the ICML I think 2 years back, that by using this signal graph processing, you can actually need not calculate these eigenvectors. You can skip that and can still get the result. So even in that case, we establish some kind of consistency results. And this is a very recent work, and which probably will upload tomorrow. So this is nothing to do with the spectral spectral methods, but most of the graphs networks you see are dynamic, right? So the spectral methods may not work very well with the dynamic networks, right? So this is our recent work. Okay, concluding remarks. So what does the spectral approaches offer? They offer very nice approximation for the problems of community detection networks with some theoretical guarantees, right? So though your optimization is slightly crazy, there is no intuition or anything like that, you still can establish some kind of guarantees. And what would you indulge in? You indulge in results from numerical linear algebra. These are all Davis-Kahan theorems, and concentration inequalities from the random matrix theory. So these are the things you use. So must read. I think this Spielman has given. I think you can straight away. You can. I'll all of you to go. I think this video should be available. He has given a plenary talk in ICML 2016 on spectral methods. It's much very easy to follow. You should take a look at it. And you can also read Luxembourg review on spectral clustering. And you all know that Anand and myself are offering this spectral algorithms course in CSE. Okay, so these are the activities. That's all. Davis-Kahan, you are? how good is